to the first session of our fall 2025 program for the Virtual Inter-University Symposium on Infrastructure Management. For those who are new to VISIM, it's a virtual symposium that is hosted by Professor Pablo Durango-Cohen here at Northwestern University. Today, Steve and Cal will be presenting their work. Each presentation should be about 20 minutes long, after which we will take questions from the audience. People can speak their questions or send them using the chat feature. I'd like to point out that this meeting is being recorded and will be made available shortly after. Thank you all for attending. And now I'll introduce our first speaker for this session, who is Steven Chuo. He is a doctoral candidate at the Chair of Infrastructure Management at ETH Zurich, working with Professor Brian Eadie. Steven's research focuses on process and data analysis to enable digitalized decision-making for railway intervention planning and prefabrication supply chain optimization. He previously worked in risk consulting for AECOM, and he received his bachelor's and master's degrees from the University of Waterloo. Steven, go ahead.
Thank you, Pablo, for the introduction. I will now share my screen. And let me know if you guys can see it. Just a thumbs up. Okay, perfect.
Yeah, that's good.
Okay. Before I start, I would like to thank Professor Durango-Cohen and Pablo for organizing VISIM. Some of our past members from our group have also presented here, and they've all expressed, it was a very good experience to get feedback from the group as well. So I'm looking forward to present my work here as well. So here I will present my research where we incorporate BIM with predictive analytics to help the decision makers plan the railway interventions. And in this context, I will first go over what the main aims of the works is. So here this is a part of a broader question on how we can enable digitalization for railway infrastructure maintenance. And this is part of the digital transformation, which we frame it more as a social technical problem, where we need to understand the stakeholders who are involved throughout the decision-making process. Here, our focus is on non-routine interventions. So, for example, we can think of it as rehabilitation or renewal or replacement of infrastructure objects. And this differs from routine intervention in a way that routine intervention are typically scheduled based on time. Whereas for non-routine interventions, these are typically triggered by a condition, let's say in a condition that requires a certain intervention that needs to be done in order to maintain the service level of the infrastructure. So with that, the three main questions or the three main goals that we're trying to answer here are understanding the planning process in the context of railway infrastructure management, as I mentioned before, in the context of non-routine intervention planning, understanding the tools that are available, whether through the state of the art within research or the state of practice within industry, how those tools enable decision making in a digital way. And lastly, which I think is the most important bits, specifically concerning the coordination between these tools, as well as the interface between these tools or methodologies and the people that will actually use these tools for decision making. What we found is that a lot of times when we're working within research, we're talking to the industry practitioners, is that we build tools or methodologies that are, of course, very advanced, that make use of advanced data analytics to help enable decision making. But there is often the lack of alignment between the requirements from those stakeholders with the tools that we developed. So here, the main hope here is to highlight how we approach that problem of how we align the requirements from the people that we envision to be the main user base of the tools or methodologies, and how those tools fit those needs exactly. So to start off with, I will introduce our mapped process of railway intervention planning. This was done through a series of interviews we've had with the staff member at the Swiss Federal Railways in Switzerland. Um, Here, this is a process that spans multiple years, multiple decades even, starting all the way from the red box here, the network development. These typically start 30 years before the planned execution of those interventions. And these are done on the national level when they want to, let's say, increase the service level of the existing network in order to meet what will be the projected future demand or increase in the future demand. For example, you can think of, let's say, a corridor between two cities. Maybe they expect the population to increase in one part and they will need to commute between the two areas. And they might want to increase the capacity by building a parallel track next to the existing corridor. So that would be an example of what would be a network development. And in the blue box here is the more typical asset management that we're quite familiar with, where the asset managers look at condition state reports or engineering office reports to plan and to define the requirements for the interventions that are necessary in order to maintain the asset in the current service level. And typically, those requirements have to be coordinated with the development interventions in a way that there will be less disruption to the user of those network. And those are done by the yellow box in the network coordination. The network manager taking the requirements from both the development and maintenance interventions, cluster them into projects or into a specific work zone where they look at different dependencies from the perspective of economics or from topological states and things like that, so that you can have synergy from the different intervention requirements from the different asset owners. And once those requirements have been clustered into projects, then it gets fed down to the green box here, where the production planners and project managers, they define in increasing granularity the sequencing of the construction of those interventions, as well as what the closure concept will look like. So closure concept is very important in the railway context, specifically because there is a constraint from the timetabling where there is a defined a schedule that needs to take place in order to meet the current demand from the customer. And those are defined by the purple box from the capacity planning team. So in this stage of time, we're talking about roughly 3 to 1 year before the planned execution of the interventions, where they need to coordinate very closely in order to define how the sequencing of the intervention will look like, but also what would the impact to the customer that use the railway network. So with that, this is the overview of the intervention planning process that we have mapped in the context in the Swiss context. And for our research, we are concerned with, first of all, the asset manager who specify the intervention requirements based on condition reports or based on engineering reports. We're also interested in understanding how we can better group and cluster the interventions based on different dependencies. And lastly, we're also interested in understanding how those information can help make an early estimate of the sequencing of the interventions that are needed within the project, but also how will the impact look like from the train scheduling perspective. So this is the context of my work that I'm going to present here. So this is an example of the algorithm that one of my colleague Hamid has presented before a few iterations ago from VISIM. This is a snapshot of what the output will look like. Where in the graph here, you see a network of infrastructure objects, and the goal here is that we want to be able to estimate on a component level what will be the interventions required. So here we can see information like the type of intervention, whether it's a replacement or rehabilitation, the expected duration of the intervention that needs to be carried out and how that affects the closure required on the possession time. But here we're also getting an early estimate of the cost, for example, so that the asset manager can plan better in terms of the budgeting that are needed within a specific planning period. So this is the output that we're working with from those predictive algorithm. But talking to the staff members, we quickly realized that sometimes it can be overwhelming or confusing looking at information in a very dense format like this. So then the question becomes, how can we better visualize this kind of information? And especially now with the rise of BIM, that's being increasingly used, especially in the railway infrastructure management. We want to find a way where we can incorporate the output from this information with BIM in a very cohesive manner. So with that said, we have the algorithms that we can estimate the condition states as well as the intervention on a component level. And the goal here is to be able to create a 3D model based on whatever information we can find, whether it's from 2D plans or from satellite imageries, and how we can connect those information on the condition states and the interventions with embed them within the BIM models so that the stakeholders can easily, play with the model itself to visualize those information as well. So here is how we have defined the scope of the work in the context of this railway network. It's located in Switzerland, composed of 30 different bridges of 4 different types, with a steel, composite, masonry, and concrete. Here we have largely relied on 2D drawings to create the 3D models using Autodesk Revit. Here we were pretty clear about the level of development that we expected the models to have. So the level of development can range from 100 to 500. 100 is a very basic model that shows the general shape of how it will look like versus level 500, which has very detailed connections, which are typically used and required for construction activities. So the models we have done here it's roughly between 250 and 300, and to us that is sufficient in the context of intervention planning at this stage of time, because we are only interested in seeing how the component level condition state and interventions would evolve over time as well. We don't really need to see how the connections will look like between the different components. So that's the level of development we have done in this railway network. Then the next step becomes how we can show this information to cater to the needs of the different stakeholders that are involved in the intervention planning process. So just to do a quick recap, so we have these 3 main stakeholders who we are very much interested in to help make better and faster decisions. First of all, the asset managers who specify the intervention requirements, typically done 10 to 12 years before the planned execution of those interventions. And here the granularity of their decision making is typically done in different planning periods in Switzerland. These are typically five years for the railway planners, but it can be longer depending on what kind of assets they are working with. Also, the network managers, who, like I said before, they are interested in clustering the interventions in a way that minimizes the impact to the stakeholders. Here they also define the specific work zones that each project would be part of. So sort of the perimeter of a corridor or within a certain region, on what interventions can be grouped into that. And finally, the production planners and the project managers who would define in increasing level of granularity the closure required to perform the interventions, as well as the sequencing of those interventions from months to weeks to days. So this is first an example of how the information will look like in terms of visualizing the component level condition state on the assets. So this is a demonstration using Autodesk Revit, and this plugin we use as well is called Dynamo, where it's able to link the information output from the algorithm and then embed them within the properties and attributes of the model elements within the BIM model itself. So here they can play with the different year, the different specific filters to really get a good sense of how the condition state will change over time. And they can also see the information on the intervention requirements on the component level. So they can see the same table that we saw in the very beginning of the presentation from the output of the predictive algorithms, information like the cost or the expected disruption or the closure required to perform the work. Also the type of intervention that is expected to be performed on those components. And once those information are defined, let's say the asset manager have already output a list of the required interventions after having gone through the engineering analysis, then the network manager can cluster those information and then optimize the grouping of those intervention requirements that they receive from the asset managers. So here, this is the demonstration of how we can visualize the output from the optimization algorithm that have already clustered the intervention requirements, and they can filter based on the planning period into the future, whether it's year 6 to 10 or 11 to 15. They can filter based on the time window, whether it's a weekend or the week, or in the evenings. They can also look at what are the components that have been clustered to which specific year of planned intervention into the future. So in this specific demonstration, the network manager can very quickly see the relevant components according to the filtered criteria as we have set out in this example. And this is not only beneficial to what they need in terms of organizing the spatial understanding of the components that are required within this specific planning period or within this specific planning year, but it is also a very effective way to disseminate this decision to the other stakeholders that are involved within the intervention planning process. And using the same type of information, the production and project managers are also able to click on any specific components of the model to look at the estimated information in terms of the time window or the type of interventions that are required on different components. And this is always aligned between the different parts of the planning process, between network management, also between the project management of clustering the project, but also looking at the actual planning of the execution of the projects. So the goal here is to really have a very streamlined flow of data and information from one part to the next. And then in terms of how they can look at the spatial temporal aspect of the same information that I showed beforehand, this is a very typical view of how they plan the construction of the interventions. So on the x-axis, so to speak, you can see the spatial, let's say, ordering of the different stations, different bridges, different assets that are contained within this railway network. And then vertically, you can see the time scale that we're looking at here. So this is the direct output from the algorithm, where we can see what kind of components have been grouped into this specific within this specific clustering of the project. And this is done on a monthly scale, but we can also incorporate the train schedule information and then look at it in the increasing granularity, in this case, in the weekly scale, to really see the impact of the planned interventions that are done on the network and what it means exactly to the stakeholder, whether from the customer, for the passenger trains or for the cargo trains that need to use this network in the evenings, for example. And we can zoom into more to really see exactly how these planned interventions on the components should be done. And this information can be exported into a table to then incorporate again back into a BIM environment. In this case, using Naviswork, where we can really see the sequencing of the interventions. So this is not necessarily the plan defined exact way of how the project should be run. This is, to keep in mind, done quite early, still quite early on in the intervention planning process, let's say 3 years beforehand, before the planned execution of those interventions. But at least this gives a pretty good sense for the production planners and the project managers to see exactly how the sequencing will look like as suggestions. But of course, once they get more detailed information and coordinate more closely with the capacity planning team, then they can define the exact sequencing of those interventions. So in terms of how all this work will fit within the planning process, these are the areas where we think would benefit from the asset management perspective, from a network management perspective, but also from the project planning perspective, where we see the use of BIM and incorporating the output from the predictive algorithms can really benefit the decision making. And just to quickly go over some of the tools that we used, we have the output algorithm where we currently work with in Excel, for example, and those information are fed into the BIM model using Dynamo. It's a plugin in Autodesk Revit. To link the information from the output of the algorithms and embed them specifically within the properties of each element within the model, which would eventually look like this when you visualize those information. And similarly, for construction planning, we have the output from the algorithm. And after incorporating the train schedule information, we can then set the defined sequencing of those estimated interventions, and then put it back towards in the BIM environment to really visualize how those things will progress over time. And that concludes my presentation, where I hope you get a good sense of how we approach the problem of digital transformation within the railway infrastructure management space, where we first try to understand how people make decisions, what are the tools they use to make decisions. And then from there, we were able to then develop methodologies and the different approaches and different digital solutions that we hope cater to the specific needs of the stakeholders who are involved within the decision-making process of intervention planning for railway management. And that concludes my presentation. Thank you again for your attention. And I'll be happy to take any questions if you have any.
If there are any questions, you can either speak up or you can type it in the chat and I can read them out loud, whatever you prefer.
Thank you, Steven, for a very cool presentation. I love the way basically you are displaying all of this information that is useful to support the planning at various levels, and it seems to be integrated pretty well. I do have a few questions. I don't know how well the engineering development that you've done, how it integrates, if at all, like kind of with financial planning, like in terms of which would be even at a higher level to really try to understand how budgets and so on can be allocated efficiently across all of these assets and so on.
Yeah, so well that's a very good question. We didn't really take that into consideration, assuming that they are able to really set the threshold required in terms of the budget allowed per year, for example, or per planning period. The goal here really was really to demonstrate how we can visualize the information output. But of course, if the budgeting changes, let's say from 50 million to 100 million, I imagine also that the way you can plan the intervention into the future and also how the clustering will look like on the network level will also look quite different. Yeah, with that said, obviously there's, a lot more sort of intricacies in terms of how we consider the constraints and specifically the dependencies of how we can group things together. Because budgeting is one thing, but also one of the biggest constraint after talking to the staff member at the railway organization was actually the use of machineries. So there's only a limited amount of, let's say, different a crane that can move around between the different stations or the different specific type of tools they need to perform certain interventions. Those are actually the biggest limiting factors in how much and how fast they can perform the interventions on a yearly basis.
If there are no other questions, another thing I was a little bit curious about. So up front, when you were describing the planning process,
Yeah.
you talked about essentially two types of interventions, some that were like planned potentially many years in advance, and then some that were reactive. And so I don't know if it happens often. I suppose it depends on other factors. But for example, when we are reacting, I think that's something that might be interesting is to have some sort, which I think is enabled by the tool that you developed, is to have some sort of list of dependencies, right? And so basically, if we do have to react to and basically intervene to do a repair, we might as well carry out some other activities that might result in in not having to disrupt the system a second time. And so, I mean, that is much more of a planning question. I don't know if you have any sense.
Yeah. I mean, we were quite careful in how we frame the context of the work because, I mean, when we're looking at reactive interventions, those we typically associate them with, let's say, a large-scale emergency that has happened, let's say from a natural disaster, from earthquake, or from landslides, and those have a much quicker time scale that I work with in order to respond to those scenarios. Um, Here, they actually have a different makeup of how they respond to those emerging scenarios, which bypass a lot of the things I described here in this process. Typically, typically which take concerning the clustering of how those interventions should be grouped together. Um, Here, the focus is, of course, mainly on the early planning of how we can plan for the non-routine interventions. But I imagine that, when they have an overview of what's to be planned on the network, perhaps something could be combined together to have a more synergy if they're going to do those work anyway. But I imagine those cases are probably a lot more rare than we imagine. But those are, I think, yeah, definitely could be a possibility on how they could use these tools in those specific cases.
Are there any other questions from the audience? Jürgen?
Steven, thanks for this very nice presentation. Maybe one short question. Now you
Yeah.
give this very nice presentation. So what are the next steps in your research? Where you think this will heading towards to?
Yeah, no, that's a very good question. So we've actually presented the preliminary results of this work already to the rail organization in Switzerland. And one of the main challenge they see in the actual use of these tools and methodologies is the integration within their own internal legacy systems. So that is a big hurdle for a lot of the translation of research ideas and proof of concepts into practice, primarily because part of the work we do is, of course, simplified in terms of the data structure, in terms of the flow of information and things like that. So I think one thing that will be quite interesting to look at least for me, when I'm more interested in having a real impact of the work, will be to look at how we can further sort of integrate the proof of concept that we develop within research into practice. This, I suspect, probably need a little bit more of a, let's say, a IT or a computer science background, perhaps. But at least from the engineering perspective, that's something that let's say, the asset managers, also the engineers, have expressed their concern about how these things could be integrated. Because, on paper, conceptually speaking, everyone's on board with it. But really, the main challenge is how we can actually integrate these results into practice in the long term in a very cohesive manner with their existing methodologies, with their existing IT systems, and things like that. So that'll be one aspect. Another aspect is we were also trying to explore how the models we developed could be integrated with VR, for example. I mean, those kind of things are, I suppose, yeah, planning for the future of eventually, if let's say every person has a headset and they can coordinate remotely in real time, everyone looking at the same model, rotating the same model to make a collective decisions and things like that. So that will be something I think could be interesting to look at as well. Also, perhaps you have a field inspection team that has a AR on a tablet. They can overlay the information that we have shown here in terms of the contingent state or the plane interventions, overlay them onto the view of the actual asset on a field, to get a good sense of how the things planned from this algorithm would translate into practice when they're looking at it in real time. So those are potential ways I see this work can be further developed. But of course, there's just a lot more we can look at as well.
If there are any more questions from the audience, otherwise, thank you so much, Steven, for a great presentation, and I'm gonna introduce our next speaker. Our next speaker today is Cal Skiles. He is a PhD candidate here at Northwestern University. He's working with Professor Pablo Durango-Cohen. Cal completed his undergraduate studies in industrial engineering at the University of Illinois at Urbana-Champaign. His current research is focused on multimodal freight systems, infrastructure management, and simulation. Cal, whenever you're ready.
Hi, Pablo. Can you see my screen and hear me clearly?
Yes.
Great. All right. So as Pablo mentioned, I've been working on a research project related to multimodal freight systems. And what we're going to talk about here today is a multimodal freight transfer facility simulation platform. And this work is done on a project funded by the ARPA-EAG program within the U.S. Department of Energy. And it's a project that we're working on here at Northwestern with some collaboration from a group at Vanderbilt. And I'd like to thank my advisor, Professor Durango-Cohen, for all of his help. So to start, we're going to go over an overview of the project as a whole, give a little background on what one of these multimodal freight transfer facilities is like, present a MATLAB Simulink model that is the simulation platform itself. We're going to go over a few modeling scenarios that show what it can do and what the different outputs can be. then present its currently available form in a publicly accessible dashboard, and then a little bit of future work. So for the project as a whole, we're looking at the entire freight transportation network of the US, and we're thinking about it from a lot of different fronts. We're looking at it as a network design and infrastructure deployment optimization. We're looking at fleet management and energy infrastructure for new technologies and just purchasing new models of existing technologies, and then also some logistics and routing optimization for understanding what paths the freight should be taking across the country. And then the module that we're going to be talking about for today's presentation is the simulation of intermodal facilities, their configuration and the operations within them. And when we're looking at one of these facilities, what we did at the beginning of this project is we went to this inland port area near Joliet, so just outside of Chicago, where there are multiple very large intermodal rail yards where containers are primarily transferred from trains to trucks to reach their ultimate destination, but also in the reverse direction of being brought to the facility by trucks and removed by trains. These facilities have these electrified wide span gantry cranes that handle the loading and unloading in most situations. They also have some reach stacker cranes that look more like trucks that drive around and handle individual containers. This area is considered an inland port because a lot of freight is directly transferred from coastal ports to the railroads and shipped directly here and unloaded like an inland port. This slide is a graphic that was posted by JB Hunt to compare two different types of intermodal freight service. And the point that I want to present here is the top case, this inland port intermodal, is where the container remains in the ocean liner shipping container all the way from its origin to its ultimate destination. And so this means there is no truck-based portion between the port and when it goes back on the rail. Whereas JB Hunt's process that they are advertising for is one where the contents of the container from the ocean liner are transloaded into one of their containers, shipped by truck to a rail yard, and then by rail to their ultimate destination. And one of the things we're considering here is making this inland port intermodal more efficient, such that these long dwell times in the port and at the intermodal ramp at its ultimate destination can be brought down and can be considered a more reliable mode of transportation. And by removing this additional touch of all of the cargo being moved from one container to another in the transloading process, it becomes a more efficient process if we can just keep it in a single container the entire way. So with this facility simulation analysis, what we're trying to do is be able to answer some operational questions for these facilities to increase their overall efficiency and make them more enticing for shippers. So a few questions to consider: what facility upgrades to prioritize if we're looking at a potential increase in volume? We could look at a number of different strategies to do so, such as increasing the number of staging spaces, the number of cranes, reducing the cycle time for the hostler trucks making these moves. Another is considering the transition to battery electric hostler trucks to replace the diesel powered and show how you can vary a number of these different input parameters. We'll look into this one in detail as one of the modeling scenarios and outputs. And the last one is, what can we do about these dwell times? How can we change specific parameters that we can control to lower these overall dwell times? And one of those is looking at a priority inbound container lane where there is less dwelling because there is not even a hostler move. And we're going to look at that a little bit as well as a modeling test. So after that site visit to those facilities, we were able to develop this flowchart to help present our concept of these facilities and make it easier to understand what's going on within them. And this graphic shows the flows of containers through these facilities. So they arrive by train or unloaded by these cranes to a staging area. They're moved by Hostler trucks from that staging area to a storage area, and then external trucks arrive and remove them from the facility. This also occurs in the opposite direction, leading to containers being loaded onto trains and removed. The other key component of this diagram is the concept of refueling or recharging. Specifically, the Hostler trucks is the key component of the simulation, but we have the ability to expand to consider the external trucks and or the vessels, such as locomotives. This is the diagram of the MATLAB Simulink model. And so this is where the simulation runs, and each of these boxes is a subsystem of the simulation, and it's where the entities are generated, the flows occur. There are a set of queues and servers that handle these flows and make it run in a realistic fashion. These connections show where the hostlers move from one subsystem to another and where the containers move from one system to another. This slide is just to show how this conceptual flowchart and the Simulink diagram have a similar overall layout. You can see kind of a similar flow through each one of these diagrams, and it gives this a little more context to what's going on since we're not really digging into it. We're going to show a couple of these subsystems quickly to give some context as well. So the Hostler charging subsystem is where we have the hostlers initially generated, but more importantly, it's where the hostlers return after making a move, and their fuel level is checked to determine whether they need to go charge or refuel or not. And that process involves it going into a queue to charge, potentially waiting and seeing how long it takes for it to charge, which is controlled by this slider and this MATLAB function block shown here. Another subsystem to see is the inbound container move subsystem, and this is where after the containers have been unloaded from the train, they are then available to be picked up by the hostlers and moved to the storage area. This process is showing where they are picked up by the hostler going into this server block. The service time of this server block is currently controlled by a function that models congestion. So how full the storage area controls the service time of the hostler. And then we can also capture hostler utilization and the total number of available hostlers throughout this process. Here's a full list of the available parameters that can be changed for these different scenarios. These include a lot of things related to the movements of the containers, so how they arrive, how they can be moved, the number of assets, the number of queue spaces or staging spaces for them in many different processes. But in the cases we're going to talk about today, we're going to look at the hostler charging subsystem. So we're going to vary the number of hostlers, the number of charging stations, the mean charging time to delineate between the diesel hostlers, the battery electric hostlers, and then the final case we're going to look at is the percent of containers via priority path. So for these modeling scenarios, each simulation is 1 week of runtime. The first scenario we're going to show is determining the number of refueling stations needed for a fixed number of hostler trucks. And then the second scenario is the reverse, determining the number of hostler trucks needed for a fixed amount of refueling stations. Both of these scenarios are tested for diesel and battery electric hostlers. And the overall objective is to keep throughput of the facility similar, and we'll show kind of a sensitivity analysis for each of these. So the first scenario, we're varying the number of refueling stations and finding how many refueling stations we need for 15 diesel hostler trucks to reach a certain throughput level. And what you can see here in this first chart is that if there is only one refueling station, the total throughput of the facility, so containers unloaded, drops a significant amount. The wait time to refuel, the median wait time increases dramatically, and this staging area queue for inbound has grown to a point where there is gridlock. And this is what leads to the drop in overall throughput. And so what we determined from this is that we need at least 3 refueling stations for 15 diesel hostler trucks. As you can see, the total throughput is level at greater numbers of stations. For the battery electric case, it's slightly more interesting because we're dealing with longer refueling times. So we have a little more flexibility in the number of charging stations. And what we determined here is that we needed 7 charging stations as the throughput is flat at greater numbers, and there is a drop off in throughput at lesser number of charging stations, the increase in wait time, and the increase in staging queues. And so the difference here is we have 25 hostler trucks, but the refueling time takes an average of 60 minutes. The next scenario, we're looking at varying the number of hostlers for a fixed number of refueling stations. In a similar way to look at this chart, you see that the throughput levels out once we reach approximately 15 hostlers, and that is how we were able to determine that 15 was the minimum number of hostlers to reach this overall throughput value. There is minimal refueling wait time considerations at these level of hostlers. And when you look at the staging area queues, it starts to grow at 15, but the total capacity of this queue is approximately 300. And so this 115 median for the entire week does not reach near the capacity. It levels off and stays consistent, showing a balanced flow throughout the simulation. The last case related to the refueling stations and hostlers is we're looking at how many electric hostlers do we need for 7 charging stations. And we considered a wider variety here, meant to show a couple different things. So the number of hostlers, we see the number of containers loaded and unloaded. So the overall throughput does increase with the number of hostlers up to the early 20s. The refueling wait time becomes significant in this mid-20s area, but we're dealing with a 60-minute average refueling time. And so this, with 25 hostlers, still leads to a total throughput similar to greater numbers and the original baseline case. The other key point to see here is that the staging area queues do grow dramatically in the lower number of hostler cases. And the one kind of new finding here is when you increase the hostlers to a greater number, we see an increase in the refueling wait time just due to the fact that we have a fixed number of charging stations. And as they go to queue, the queue gets longer with more hostlers going to charge at different points throughout the process. All right, and then the last scenario that I want to present is looking at that priority lane. And how this priority lane is set up is where the cranes unload the containers currently is into a staging area where the hostlers pick up the containers and move them to a storage area where they dwell. And what we wanted to look at was, what if the hostler move to the storage area didn't occur for some percentage of the containers flowing through the facility? And so how this would happen is the external trucks that are arriving to pick up containers would come to their own priority staging area that the cranes are able to directly unload containers into. And so this is kind of like a perfect situation case. As we increase this percentage of priority lanes, we're seeing how much more the throughput of the facility, without changing the number of cranes or the service time of the cranes or the arrival rate of containers, how much can the throughput of the facility change just by better timing the crane unloading of containers and when it gets picked up. So if it were perfect, the crane would unload the container and the external truck would come to get it right at that point. And then we would have minimal dwell time and not even use a storage space for that container and have lesser need for a hostler. And so what we found in this set of results is our base case is nothing goes the priority lane and we have 15 diesel hostlers. So that was the baseline case from the previous scenarios we were discussing. And what you see there is 9,142 inbound containers are unloaded. The comparisons here are we increase the priority percentage to 10. We keep the hostlers the same. The total number of containers unloaded through both lanes, both the priority and the regular lane, has now increased to over 9,700. And this did not involve any real change in the assets required. We still had 15 hostlers. We still had the fixed number of cranes, fixed service time. But those hostlers can now focus on keeping the regular staging area clear while the external trucks handle this 10% priority line and the flow picks up throughout the facility. For comparison, if we drop one hostler but keep that 10% priority, the total throughput is now 9,500, which unsurprisingly is lower than when there are 15 hostlers, but it is significantly higher than the 15 hostlers, 0% priority case. This next column is we've dropped it to 12 hostlers at 10% going via the priority line. And the point here is to show that there is a point at which the number of hostlers becomes insufficient. And so now the throughput has dropped significantly in the inbound direction, and it is not a worthwhile investment to plan for fewer hostlers at this priority level because you're not getting the same level of throughput. And then the extreme example, if 20% of the flows were to go via the priority lane at 12 hostlers, we do see an overall increase in the throughput. I'm still working on exactly the best ways to capture this information, but I wanted to show some preliminary results related to this concept. All right, so our project includes a publicly accessible dashboard with a set of tools. The URL is here. It's also on the last page of the presentation. And the intermodal facility simulation is an example of running this model. And so it's similar to the first scenario I presented, where you set the average hostler refueling time, the number of hostler charging stations, and the average hostler cycle time for moving a container. And we have a fixed number of electric hostlers compared to a fixed number of diesel hostlers. So there's a baseline case in blue here, and then the battery electric case based on your inputs. And you could compare the wait time to recharge in this first graph throughout the 1 week of simulation, and then the inbound staging area Q throughout the simulation time in the second graph. And what you're seeing here is that the wait time levels out to about 10 minutes on average for the battery charging case. And then in this case, we're seeing a relatively similar leveling of the amount of staging spaces in use, and it shows a balanced flow throughout the simulation. So the next steps, once we've been focused on the intermodal rail yard and the operations within one of those, we hope to expand to a coastal port and handling a little bit more information, such as mode split between truck and rail for those for the freight coming through. And then we're also considering inland waterway terminal facilities, since we've discussed that for a number of other parts of the project, and we'd want to understand the operations within those facilities. Thank you all so much for listening. Please let me know if you have any questions.
Thank you, Cal. If there are any questions, feel free to speak up. Jürgen?
Yeah, thanks for this very nice presentation. I have two questions. One might be more for clarification, which is, so you used some kind of probabilistic input, or you set your inputs fixed? And then I guess the follow-up question would be, if it's a deterministic approach, what would you expect if you change it to a probabilistic approach?
Yes, very, very good question. So there are a set of fixed parameter constants, and then I didn't go into this detail, but this table was meant to show that there are a set that are means for an exponential distribution, just to keep it relatively simple on the number of parameters needed. And so like the service times are based on these exponential distributions. The inner arrival rates are based on that. And so there are a lot of things that are deterministic, and then these are variable. And your question was, do
you
if they
see
were
any
to,
significance with this probabilistic approach? Because again, you're taking here the mean, but it might be, if you have an exponential distribution, that you have some extreme values, which I guess causes some backlogs. Probably that's the normal case where backlogs are appearing if a lot of bad things coming together at the same time. So how would you, do we see something like this? Or are you looking at these extreme cases, which might be the more uncommon ones, but probably the one which have more severe impact towards the operation of these facilities?
Yeah, when it comes to the extreme cases, I think you're making a very good point, and it's the tracking of these different output statistics during the simulation runs. We're able to see what is going on pretty clearly, and the extreme outliers are important, but I haven't seen overall impacts on the running of the simulation that are that extreme. But it's certainly something I probably need to look into more.
And maybe another question, since we're on this slide, how do you validate this model? Now, it seems like there's a lot of assumptions and things you have to set there. So how do you validate this complex machinery of you developed?
Yeah, so a lot of it is based on the facilities we got all of the information from. And so most of the key parameters are based on one of or both of the rail yards we toured and got the information from. And then we have some like total throughput data to help match up against. We can't do it for every statistic because we just don't have that much data. But when it comes to the overall throughput and the train arrival and departure rates, we can see if they're aligning overall. So it's not, I wouldn't call it perfect, but it gives us a good idea of what's going on.
If you have time for one more question, maybe I have my last question. Now you looked, I guess, more through the throughput rate, but I guess at the end of the day, it's some kind of monetary incentive these places have. Now, the more you put through, and you have to invest into either fuel consumption or electricity, you intend also to look into this monetary impacts of making decisions on these systems?
Definitely. Definitely, yeah. We have a number of cost and emissions-based aspects of the project, and I just haven't gotten there yet with the simulation. But it will be a key point is determining the cost necessary for these expansions or investments. These initial cases were kind of to show if your goal was to transition to battery electric hostlers, right? And you just wanted to know how many you needed. That was the case we were initially trying to answer. And then you're right. When we get to the exact expansion requirements, or if we're claiming there's going to be a certain throughput increase, we will need to have a more clear cost and energy use aligned with it.
Are there other questions, Steve?
Yeah, thank you, Cal, for the presentation. It's very interesting. I just have two small questions. The first is, in these kind of simulations, you typically expect certain results. So was there any output that was off the norm of what you expected? And if so, what was the reason? Or were you able to justify why those scenarios or why those output happened? And the second question is, considering the runtime of your model, how would you go about, let's say, improving the runtime, or would you do a different approach, like using an analytic model, for example, to address this problem?
For the first question, the modeling of the charging system led to a few different results that were unexpected. So the process for the Hostler charging is that the hostlers are modeled as entities and the containers are modeled as entities, and the hostlers and the entities combine and then split when they're picked up and dropped off, and the hostler wait times were not aligning with expectations for a long time. And the issue with it was that the way the battery or fuel level was being modeled was only captured when they had picked up a container and were moving with that container. And so I had a number of hostlers, and the mean charging time were not impacting the wait time like I expected with how much throughput was going through. And so what we were able to find was that the way the model was impacting the fuel level was only occurring when they picked up a container, and not any time that they were moving. I don't know if that was exactly your question, and then sorry, what was your second question?
Oh, because you mentioned, I think the runtime was 1 week.
Oh,
For
sorry,
the
yeah. No,
simulation, yeah.
that's me probably using the wrong terminology. We were running a week of simulation. It runs in about 90 seconds to 2 minutes.
Okay, yeah, because I was expecting
Yes.
yeah, okay, understood.
Thank you for that clarification.
Okay, yeah.
I need to be more clear on that.
No worries.
Yes. So if you were to go to the online dashboard, this runs in less than 2 minutes.
If there are no more questions, thank you to both of the speakers, and thank you everyone for being here, for asking questions. And with that, we conclude this session. I look forward to seeing you on the next session on the first Friday of next month of October.
Thanks, Pablo.
Thank you.
Thank you for organizing.
Thank you, guys.
Thanks. Bye.